Okay, hello. Today we are going to talk about waves, right? So here from the website Flipping Physics, which by the way is pretty cool and you should visit, you will see a GIF of a wave profile traveling across the screen. Now note that the shape is moving from left to right, but the energy or the particle or that little sticky tape is only moving up and down. Okay, so you can see that energy is traveling but not the particle. Particles only move up and down. All right. So because waves is defined as an energy transfer, so here you can see a wave pulse, which sometimes we will also include in our study, but we will focus more on periodic waves, okay, because that allows more analysis. So when it comes to wave classification, there are two types, the longitudinal and the transverse wave. Notice that the disturbance or the oscillation of the particle is parallel to the direction of propagation for longitudinal. Keyword here is parallel. And for transverse, the direction of propagation and distribution is 90 degree. Okay, so transverse is 90, propagation and disturbance. Longitudinal is parallel, disturbance and propagation. All right, so now we're gonna write down the notes, okay? And this part is a bit speed up. So as you can see, this part of your notes, you will see the direction of oscillation of your particles is vibrating up and down. And this is your wave particle, all right? And the direction of wave propagation, again, is left to right. So if you look at these two things, they're actually 90 degrees, hence perpendicular. So transverse wave is when the direction of propagation or direction of oscillation of your wave particles is perpendicular to the direction of wave propagation. Or you can also call this the direction of energy transfer, which brings us back to the first point. The definition of wave is transfer of energy from one point to another. If this is too fast, you can always pause the video and copy. Okay, keyword for today is perpendicular for transverse. So these two things are 90 degrees. All right, so the second part, you will find an example for longitudinal. If you see some shaking, I'm probably changing pen colors. I'm actually recording a voice over the video. So for longitudinal, let's check out the bottom diagram. You will find that the wave particle is oscillating left and right. Okay, and the direction of wave propagation or energy transfer is also, again, left to right. So these two are actually parallel. Okay, and because they're parallel, we classify them under longitudinal wave. So transverse propagation and oscillation 90 degree. Longitudinal, direction of oscillation and direction of wave particles. The oscillation of wave particles and the direction of energy transfer, if you want to write a bit less words, is parallel. All right. So after this, I'm showing you a GIF. Okay. So in this particular GIF or simulation, I'll post the link for you at the description of the video. Okay. So you can play with it if you want, but you can see now when I turn on the water wave, you will notice that the water wave is propagating. Hence, wave is defined as the transfer of energy outwards. All right, so that was the top view. Now we're going to look at the side view. You can see the water ripples kind of like traveling again from left to right. All right, so all this not fun enough, so I'm just going to include a graph because what is physics without some graph? And you will notice that this shows you a picture of what is happening on the water surface. They are mirror picture. So if you look at the bottom or the x-axis, this is defined as position. Okay, so which means at every single position where the water level is. All right, so you can see the wave is traveling outwards. Of course, the amplitude will decrease because energy will decrease as it travels further. All right, so I'm just going to play around with the settings a bit. Again, links, you can find the link for this simulation. You can play with it on yourself. So you will notice that as I vary the frequency, when the frequency is small, the wave is less energetic or more sluggish. So it's probably important to remember that frequency and amplitude will affect the energy of the wave. The larger the frequency, the more energy. The larger the amplitude, the more energy. So you can see when the frequency increases, there's more rippling of your wave particle. So here I have kind of like a CRO thing, and it's against time. So this is connected to the time base. It is measuring the movement of a single wave particle. Okay, so maybe the black one is easier to see. So you can see particle at this particular position where the hand is, the wave is actually moving up and down. Okay, the wave particle is moving up and down. If I move closer to the wave source, you can see the amplitude increasing because the energy is greater closer to the wave source. So check it out. You can find that this particular particle at where the hand is oscillating up and down. That's why this is time. Although the shape looks very similar, okay? So it's probably useful to really think about in what ways are both graphs different. Here you find light, again, just a simulation of a light wave, green light. So you can see that it's very slow. Light doesn't take that long to reach the screen. And as usual, this is the graph plotted against position. Okay, and now the interesting one is actually a sound wave. But before that, again, I played a bit with the lights. Okay, so you can see blue light is has a higher frequency and red light have a lower frequency. This is also transverse. Particle up and down, but traveling outwards. Okay, so direction of propagation is 90° to direction of oscillation. So in this case now, we're going to play a bit with sound wave. All right. And the thing about sound wave is I think you know the basic idea that it is the vibration of particles. So here you can see particles just freely vibrating, but the loudspeaker haven't turned on yet. Okay. So now I'm going to play the loudspeaker. But if you look at the graph, right, this is actually plotted against pressure. Now let's observe what happens when I press play. Okay. So you will find that number one, when this happens, there is a single pulse, and all these particles will vibrate and adjust to that boom, that sonic sound wave. Okay, so now I'm going to again show you a single pulse. Note that the particles only oscillate left and right. Okay, so the profile travels out, but the particle also oscillate left and right. So traveling outwards, but the particle is also moving in this direction. Pretty cool, right? So this is a longitudinal wave. Direction of wave transfer, you can see traveling out, but the particle is also oscillating out, not oscillating up and down. Okay, so I'm just gonna show you a consistent sound wave, like the sound wave that I'm hopefully recording right now. All right, so you can see from here, as the sound wave move, you can see there are places where the particles will come together. So there is where the pressure is high. So like here, the pressure is high, the pressure is high. And there are places where the particle will move away, then the pressure is low. Let's say I want to look at a single gas particle. Once again, I'm putting at this position. I should be able to find the trace. And of course, because we have two probes, when we put them at separate positions, the particles might not always be moving in sync. So from here, you can see that they have a slightly different angle between them. Okay, and later we will talk about how to describe all these properties. But this one is just to give you a visualization to help you understand how sound wave move. The particles only travel in and out, parallel to where the wave is spreading. Okay, so this is just a simple side view and top view. So yeah, go down to the link and try it out yourself. You can pause the lecture and come back later if you want. All right, so in and out this way, and the wave tracing goes out. So to make it less messy, we are now just going to look at a graph of one single wave particle. We choose one and we look at it. We already know that it's going to oscillate up and down. So as it oscillates up and down, you will notice that this particular trace actually follows. It goes up, comes down, goes up. So it's the same as looking at a single particle here. It goes down, comes up, goes down, come up. All right. So we're going to now try to label all these important properties of wave. Okay, so the first one that we're going to look at is amplitude. Amplitude is the maximum peak, the peak position measured from the center or equilibrium position. So amplitude here, Sometimes we use uppercase A, sometimes we use lowercase, especially if we want to involve area in our calculation, because area is uppercase A, amplitude also uppercase A, confusion 10,000. So here you can see that there is a peak, okay, and there's also a crest, so maximum and minimum. And the distance between two consecutive peaks, we will call this a wavelength, okay? These terms should not be new to you. So how about sound wave? So sound wave, we have places where the particles are far apart, we call it rarefaction. And when they're close together, we call it compression. When it's far apart, the pressure is low and the air particle is further apart, okay? When it's close together, the pressure is high, the air particles get squished together. So you have places of air particles congregating together. We call that increased pressure or area of high pressure. All right, and then you have the other side where the air particles are further apart, and this is where the pressure decreases. So if you want to measure wavelength, right? Okay, there are many ways to measure wavelength, but I think you can probably tell we will be measuring somewhere. Okay, so this area somewhere in the middle, so maybe we will probably take the area of increase and decrease pressure, or the position, take the middle point lah, easier. So we'll take the midpoint from decreased pressure here to the subsequent one, all right, the closest one that is nearby. So the distance between these two, rarefaction and rarefaction, is lambda. Compression and compression is also lambda. All right, so past me will now label them for you on your diagram. Okay. So yeah, so if you remember the graph that we had, we will now have two types of graph to describe waves. All right, so I'm going to draw the first one, and the first one here is displacement of wave particle y and time t. Okay, so the displacement of wave particles here is actually, we look at one single particle and see how it travels over time. Okay, so I'm just going to roughly plot out using my stylus the sine curve. I've already sped up the video, by the way, so you're not bored lah. You got some like background music to listen to entertain yourself as you see me sketch a sine curve. Quite okay, practiced a bit. All right, so we are looking at a single particle and where it is as it travels up and down. Okay, at different time, the particle will be at different position. All right, so as usual, the easy way out is to look at this one as time. So time meaning one complete cycle is known as one period. Okay, so you can measure time t here to here, or it can be from here to here. Now, if you're good in trigo, I will just tell you period here would be 360 degrees. So you can see what we're graphing is the position of one single particle against time. Okay, so at different time, the particle will be at different position. So that would be the second graph down here. But this is actually like a video. If you look at a single particle, this is taking like a video of the particle traveling up and down. We just look at one single particle. But sometimes we want to take a photo, or we want to see the entire wave profile. So this now, if you look at the x-axis, it has changed from time to the position of the wave particle x. Okay, means different wave. We are taking a photo of many wave particle. The first case, we are taking a video of one wave particle. Later, I'll write it down for you in the notes. All right, so we actually have a same shape. Again, we are assuming that there's no decrease in energy. Okay, just now in the GIF that I show you, there's a decrease in energy. All right, so again, you'll get a sine curve. It can be a cosine curve, really depends on where you start measuring. But again, 360 degree or one complete cycle, all these are known as lambdas. Okay, so lambda here is known as the wavelength. All right, so for the first graph against t, we are taking video and observing one single particle. The second graph against x, we are taking a photo or a snapshot of the entire wave profile. Okay, once again, you can pause the video. And now we're going to write down some key definitions now. Okay, amplitude A is known as the maximum displacement of the wave particle. Now, the more precise you can be for A-level definition, the better. So displacement of what wave particle measured from where? Equilibrium position. So equilibrium position is as if you never turn on the wave source. You didn't turn on the tap, you didn't turn on the speaker. Where would the particle be? Zero lah, zero. My favorite number is 0. All right. Wavelength is known as lambda. Okay. So as you can see, it's the length of one complete cycle. But because it is a length, so we are going to define it as distance. Okay. It is distance between two consecutive. Remember, we take the next one, not the one after the next one. Two consecutive wave particles that are in phase. Now, in phase here is a very important term in this particular chapter, because to understand what in phase is, we need to look at this diagram again. So you can see, right, the red and blue is obviously one wavelength apart, okay? And as you can see, this is in phase. They go up and come down together. They go up and come down together. So if you're in phase with my lecture, you are paying attention as I talk to you. Go up and come down together. All right, so this is in phase. They travel together, in sync. So you could be thinking, Miss, these two also in phase. Yeah lah, but it's not the subsequent or the consecutive one. It is the next one. So although it is in phase, it is totally not lambda. Okay, we need to put them close to each other like this. This is lambda. All right, so again, if I put them at the same place, the phase angle is 0 lah. So sometimes we like to play a bit, or I was playing a bit, okay? And I begin to move the particle because in phase means move together. Then move in the opposite direction, we will call it anti-phase. So in phase would be moving together. The angle is 360 degrees. Those of you who are good in maths, see the distance between the red and blue is 360 degrees. Okay? And see, they move up, they move down together, and the distance between this red and blue particle would be lambda. So you can play with this. Click the drop-down menu, adjust the stuff. Okay. So now I'm going to adjust a bit by changing the position so it's not exactly 360 degrees. At least I think the past me will do that. All right. So right now I'm placing them 180 degrees apart. I think eventually I'll get there. Actually, this interface is a bit hard to use. You need to click on the dot and then you click on where you want to be. And there we go. These two are moving out of phase because they're totally opposite direction. You can see, right? Because the angle is 180 degrees. Angle or the distance between the blue and the red dot. Don't be confused with me when I interchange the idea of angle and distance, because the particular graph right beside the circle is against position, so it can be distance. It can also be angle, because all of these are sine and cosine. Once again, I've adjusted so that the separation between both reference point, red and blue, is lambda. Okay, so we're gonna, hopefully that you understand what that means in phase. I'm gonna write that down. When two particles are moving together with the same motion in synchrony, you know. All right, so now we're going to talk about period. I think you all know this. Time taken for one complete oscillation of a wave particle. And frequency can be calculated with 1 over t, number of complete oscillations in 1 second. All right. So the wave speed here, because it's constant, we can use the equations distance over time. Okay, so whenever we look at distance, right, over time, I'm going to consider, because the speed is constant, right, so you can use distance over time. If the speed is not constant, you better don't use this equation. Okay, because it's accelerating, you will have to use your kinematics equation. So anyway, we are now going to look at the single wave profile and assume that the wave profile travel a distance of lambda. And the time taken for the wave profile to move lambda will be the same as a period. So we will transition now to look at this. You will notice that the time taken for the red particle to move up and down, just nice, the entire gray color wave profile has shifted from left to right by 1 lambda, which is about 4 boxes. Okay, so once again, when it goes one cycle, let's say up and then down, it will move 4 boxes. You really need to try this out and stare at it until you can see it. Or maybe you can ask me again. All right, when we are live in class together. But the whole idea is when one particle cycles up and down one time, the whole wave profile has shifted from left to right by 1 lambda distance. So we're going to write that down. For t is equal to 1 period, wave profile traveled lambda. And because f is equal to 1 over t, you can substitute and get v equal to f lambda. Sorry, that was a little bit fast. Okay, so now we're going to talk about energy, but we prefer to use intensity to describe energy, which is defined as wave power per unit area. So this is P over A. And all this, right, description, we prefer to have it in intensity because it encompasses a few things. For example, power of the wave or energy of the wave depends on number 1, amplitude square, as mentioned to you before. Number 2, frequency square. Okay, all this will be shown in your A2, but right now you need to know this as facts. Okay, and area is also proportional to the radius square, right? The larger you are, the wave will have to spread out further. So putting it together, you will get I is proportional to A square F square over R square. Okay, and finally, phase relationship, I briefly mentioned just now. We will use the symbol delta psi, but generally I use ratios in doing this. Okay, so I'll find the equivalent of 360 or 2 pi. Okay, so 1 lambda is 360 or 1 period is 360. And then use ratio. For example, if 1 lambda is 8 meter, so it's 360, then 3 meter is delta psi. I'm pretty sure you can do this. Okay, so yeah, I will show you some examples in the next video. But today, this is what we learned. So stay tuned for the examples video. But today we have learned that wave is energy transfer. We can classify wave into transverse or longitudinal. Okay. Number 2, we know that we can graph the wave with 2 different x-axes. One is time, one is position. They describe different things. One is for period, one is for wavelength. Okay, so amplitude, wavelength, period, and frequency, all these key definitions, and also wave speed. So wave particle speed, this one is in A2 and it is not a constant. We will be doing calculus well and proper in your A2 later. So we talk about intensity and phase relationship. It's a little bit rushed towards the end, but you can only understand those things at the end of the wave, probably at the end of the examples that I will talk to you about in the next video. So see you there.